Okay, so let's now answer those whys that we came across in the proof of Riemann's theorem, theorem 828. So we are going to recall the whys one by one and see how we can answer them. So this solution, let me just simply write those parts from the proof where those whys occur. So at one stage of the proof, we had this thing, the sets A plus and A minus are both infinite. And it was asked why. So this is one thing, the first why, and then there is another one, the sums summation AF plus of M as M varies from 0 to infinity and summation AF minus M as M varies from 0 to infinity are both divergent. Where F plus from N to A plus and F minus from N to A minus are increasing bijections. This is the second why, and both these whys have already been answered in the lemma that comes before this theorem. In proving that lemma itself, these whys were answered. So accordingly, we are going to write both these whys, let me write like this, have already been answered in the proof of the lemma that comes before this theorem, theorem 828. I think it's lemma 827, it should be, but this also you understand. The item that appears before this theorem is that lemma, which we need here in the proof of Riemann's theorem. And then, before we mention the third why, let us go back to the definition of the sequence Ni that we have in the proof of Riemann's theorem, where we have those two things, case 1 and case 2. So let us recall that first. So case 1 was this. If this finite sum where I varies like this is less than L, I think this was case 1, less than L, yes, then the term Nj in our sequence is defined to be the minimum of the set of all elements n in A plus such that n is not equal to Ni for all natural numbers I less than j. So this was case 1. And case 2 is just this. If that same sum is greater than or equal to L, then Nj is defined to be equal to the minimum of all those elements in A minus for which that same condition is true. Now the third y is about these two things, case 1 and case 2. And the third y states that both the cases occur infinitely often. Both case 1 and case 2 occur infinitely often. And why? What is the reason for that? So now we have to justify this why. And in fact, in the text it was given as a small hint that prove by contradiction. So that's what we are going to do. Suppose that case 1 occurs only finitely many times. So this happens only finitely many times, and for all other times the case 2 is the case that keeps on happening. So that means this sum or these sums, as you change the value of j, almost all of them are going to be greater than or equal to L. Only finitely many j's are there for which these sums will be less than L. That is our supposition. So that means starting from some stage n, all such sums are going to be greater than or equal to L. Hence, there exists some natural number capital N such that these sums are all going to be greater than or equal to L for all j greater than or equal to n. So this is just simply a simple consequence of our supposition. But now what can we say from this? Now, a natural consequence of this thing is that this sequence, next what I am going to write, will be a decreasing sequence. This implies that the this is a, well, should I consider n or n plus 1? Yeah, I can consider n, okay, no problem. This is a decreasing sequence which is bounded below by L and hence is convergent. But why? Why does this imply that this sequence is decreasing? That is because you see, okay, what is the nth term of this sequence? The nth term of this sequence is just this. Nth term means actually this is the first term because j starts from n. Fine. So because of this thing is greater than or equal to L. So that means if you want to define n using the definition that we have which involves case 1 and case 2, so then this falls under case 2 because this sum is greater than or equal to L. So n will be the minimum of this. And because of that, actually nn is what type of label is nn? What type of suffix is nn? Since nn is coming from A minus, minimum of this set means after all nn is actually in A minus. It's an element of A minus. And that is why ann is less than 0. it's a negative real number. You go back to the definition of the sets A plus and A minus. A plus is the set of those suffixes for which the corresponding terms in the series, original series, are non-negative real numbers, and A minus is precisely the set of those suffix values for which the corresponding terms are negative real numbers. So that means if you write the next term of this sequence which comes after this, then that will just simply be this which is actually nothing but this term plus a n n. So that means you are adding a negative term, so it actually decreases, and this keeps on happening. If you then consider in n plus 1, then because excuse me, this sum is also greater than or equal to L due to this condition, in n plus 1 is also going to be, whatever it is going to come from A minus, because of which a n plus 1 is also going to be a negative real number. So when you add that to this to get the next term in this sequence, that is going to be even smaller, but all of these terms are greater than or equal to L. So it's a decreasing sequence that is bounded below by L. So we know that such sequences are convergent from the theory of convergence of real sequences. So that's why this sequence is convergent, because of these things. But it's a sequence of partial sums of an infinite series, and so that series will also be convergent. Hence, the series summation a n I, where I is just any natural number, is convergent. Strictly speaking, the sequence of partial sums of this series is actually not this, but this is a subsequence of the sequence of partial sums of this series. Why? Because let me write that also. Note that the sequence of partial sums of this series is this, of which this is a subsequence. And in fact, this is not just any subsequence of this, but one which differs from this only in finitely many terms, namely the terms starting from 1 to n capital N minus 1. And in order to make everything absolutely rigorous, you can in fact consider this capital N to be not 0. I mean, this capital N comes from that part before because of our supposition. So that a capital N can of course be considered to be a positive natural number. Okay. So that means, because this note one thing, convergence of a subsequence does not imply that the original sequence is convergent in general, but this is a special situation in which the subsequence only does not have finitely many terms of the original sequence in the beginning. If you remove these first terms corresponding to j equal to 1, 2, 3 up to n minus 1, then you get this subsequence. Because of this difference in only finitely many terms, convergence of this subsequence implies convergence of the original sequence. And this is the sequence of partial sums of this series, and that's why this series is convergent. Okay, but now the thing is that its own convergence implies that if we remove finitely many terms from this series from the beginning, then that resulting series is also going to be convergent. This is also convergent. Okay. Now we are going to claim something else about our original sequence in I, which we have in the proof of our Riemann's theorem. We now claim that the sequence in I, where I varies from n plus 1 to infinity, is strictly increasing. And now, after writing this, I remember that I have forgotten to write something. This is actually not the third y. This is the fourth y. Before this, there is another y, which, let me write that here. It is awkward, but what can I do? I forgot. Even before proving that case 1 and case 2 occur infinitely many times, we have this other y. The function, this is injective. Why? So let me answer the why here itself. It's very small. It follows from the definition of the sequence Ni that Nj is not equal to Ni for all natural numbers I less than j and all natural numbers j. Do you see why? Because you go back to case 1 and case 2. Of course, the definition of Nj either falls under case 1 or case 2. In any case, Nj is this. Nj is the minimum of A plus if it falls under case 1 such that N is not equal to Ni for I less than j. So since Nj is the minimum of this set, Nj after all belongs to this set. It's an element of this set. So it has to satisfy this condition. So that condition directly tells us this, and this is true for all j. And if it falls under case 2, then also the condition stays the same. The only difference is that it now comes from A minus. Okay, so because of this, the map is injective. I hope you can see why. That's because what do we need for injectivity of a map? That if the inputs are different, then the outputs are also different. Say your inputs are natural numbers I and j which are different, then obviously they are going to satisfy one such inequality. Either it's I less than j or j less than I. If it is I less than j, then you already know that this is how Nj and Ni are different. And even if I is greater than j, then you will have Ni here and Nj coming in this set. Then also they are different. So that's why the map is injective, and this is how we have the third y. So the fourth y is what we are answering now. And I remembered this suddenly here because now I am going to need this injectivity. Okay, so we are now, what are we claiming now? We are now claiming that this sequence, note that this sequence is not the entire full sequence, it's only a part which starts after some stage, namely from n plus 1. So it is now strictly increasing. So we are going to prove this by induction. Since n plus 2 is equal to, let's just use the definition of n plus 2, and you recall one thing. This we have already seen, so I can erase this part. So according to our first supposition, we have this condition. For all I greater than or equal to n. Under this condition only we are working. So that means if you take, well, it's not I, it's j. I don't remember there. If I have written I, please change it to j. So if I now put j equal to n plus 2, which I can do because n plus 2 is greater than n, then this is also greater than or equal to L. So that means n plus 2 will be defined using case 2. So that's what we are doing. It's the minimum of a minus such that n is not equal to ni for I less than n plus 2, which is also, the same thing can also be written like this. It's the minimum of a minus difference n naught n1 n plus 1. Because it's the minimum of those elements in A minus that are not equal to any of these, that you can see from here, the same thing. So because it's the minimum of this set, so it belongs to this set in particular, it's an element of this set. So since we have this n plus 2 belongs to in particular, for some reason I can't seem to write tonight. In particular, n plus 2 also belongs to this set. Where we have just removed n plus 2 from here and we have gone only to this element. But do you see why? That is because this difference is a subset of this difference, which in fact itself is a consequence of the fact that this set is a subset of this set. So when you take difference, the containment relation gets reversed, which implies, so if this n plus 2 belongs to this set, then it will be greater than or equal to the minimum of this set naturally by the definition of minimum. So n plus 2 is greater than or equal to the minimum of this set. And we already know what this minimum is. This minimum is nothing but n plus 1. And how are we so sure that n plus 1 is the minimum of this? It comes from case 2, and case 2 because n plus 1 actually belongs to A minus. You go back to the condition that we have from our supposition where we started all these things, you will realize that n plus 1 belongs to A minus. In bracket, let me write that. Note that n plus 1 belongs to A minus, since everything comes from that condition. This is why. So we now have proved that n plus 2 is greater than or equal to n plus 1. But now combine this with the fact that the association between j and nj is an injective function. So we cannot have equality, we should have strict inequality. Since the function that maps j to n, and this is why we need the third y answered first before this, is injective, we have n plus 2 strictly greater than n plus 1. So in trying to prove that that sequence is strictly increasing, this is our basis for an induction proof. Now assume that n plus 1 is less than n plus 2, which is less than n plus 3, and it goes like that till this way. For some positive natural number I. So this is our induction hypothesis. Actually we are using the strong induction. But then the induction step is just like this one. Since n, so we need to conclude something about n plus I plus 2. Okay. N plus I plus 2 is equal to, keep in mind that we have been able to use all these things consistently because we know that all these inequalities are going to be satisfied. All of such sums are going to be greater than or equal to A, because of which n plus 1, n plus 2, all these things actually are going to come from A minus. So in their definitions, case 2 is going to be consistently coming. There is no exception to this because of our supposition. So that's why here also we know that n plus I plus 2 is going to come, is going to fall under case 2. So that's why its definition is also like this. N is not equal to Ni for I less than n plus I plus 2. But now that thing, just like that calculation, so this now becomes the minimum of A minus difference n plus I plus 1. Since we have this, So n plus I plus 2 belongs to this set. In particular, it belongs to this. Again, this difference is a subset of this difference, that is why. Hence, n plus I plus 2 is greater than or equal to the minimum of this set n plus I, and that is equal to n plus I plus 1. That again we know that n plus I plus 1 will fall under case 2, and that's why this is the minimum of this set. So we have now proved that n plus I plus 2 is greater than or equal to n plus I plus 1. But again, injectivity of the function then implies this is strictly greater than this. So our claim now follows by induction. But why do we need to have this fact, or why do we need to consider this fact that that sequence is strictly increasing? Now we are going to come to that. So now we are going to go back to those series. So let us do it in this next paragraph. Okay, since this series is convergent. In fact, that's what we concluded there, right? This series is convergent, and by the previous lemma, the sum is not conditionally convergent. The series ANI where I starts from n plus 1 must miss infinitely many terms of the sum. Okay, now there are a number of things to understand here. I discussed about this while proving this lemma, that what is it that actually means for this series to not be conditionally convergent. Keep in mind that in A minus we have precisely those suffix values for which all these ANs are negative. So not conditionally convergent means what? And in fact, convergence of this means what? You see, since it's just a sum, if you want to say that it is convergent, you can only say that using some sort of bijection. First, you consider some bijection between n and a minus that will turn this sum into an infinite series. For that bijection, this sum will be turned into this infinite series. And then you can speak about its convergence because it's an ordinary infinite series. Not conditionally convergent means, in this case, having no such bijection for which this will be convergent. And that is because if you have even a single bijection for which this is convergent, maybe for some bijections it's not convergent, maybe, say just for the sake of argument, assume that for some bijections the corresponding series is not convergent, but you have one bijection for which this is convergent. But then convergence of this series actually also means its absolute convergence. Why? Because the terms, all of them have the same sign. And this is why if that happens, then this becomes absolutely convergent. And then due to rearrangement, the other bijections that you are saying may exist for which this series is not convergent, then cannot exist. So that's why being not conditionally convergent means no matter what bijection you choose, the corresponding series is going to be divergent. In particular, this arrangement, it is actually not taking into account all the ANs possibly, but some AN. But still, this particular arrangement of the terms, these ANIs all are after all coming from, coming because of the suffixes only coming from A minus. We do not have any NI here that comes from A plus. So all these ANIs also are negative real numbers. So that's why we are saying that since this is something that we have got is a convergent series, whereas the terms that you see here are actually coming from this series. So that's why this has to miss infinitely many ANs from here. Otherwise, what would happen? Otherwise, you can just supply those finitely many ANs that this one is missing from here to this one and get such an arrangement of this sum so that that series is also convergent. You see, this is already convergent. If you supply those missing ANs, then this will turn into one such series. But if those ans that you have to supply are finitely many in number, then convergence of this would automatically imply that the slightly larger series, if I use that term, that is also convergent, but then this cannot be not conditionally convergent. It will then have to be conditionally convergent and hence also absolutely convergent due to all the terms being negative, which would contradict lemma 827. So that is why infinitely many n's must be here, for which an is it should not be found here among the ANIs. They are not to be found. That is, there exist infinitely many this such that this is what we mean. Because otherwise, let me just again repeat, because I think whatever I said just now is maybe a little bit confusing. This is convergent. You just think of it in simple terms. This is convergent, and the ANIs that you see here are actually coming from here. Maybe not all ANs are available there, but some. So how many ANs can this one miss from here? It has to be infinitely many, because if it is finitely many, then you can just simply supply those ANs there, and that resulting series would also be convergent because finitely many. So that is why this should happen. And now what is the consequence of this? Now we are slowly inching towards an actual contradiction, a dead end. So the thing that happens here is this: among these n's, there is at least one n satisfying and well, but why? Keep in mind that the n's that we are talking about here are all coming from A minus, and they are all different. They are different from all the ni's that you see here, for which I varies from n plus 1. And there should be infinitely many such n. So clearly, because of this infinitude of the number of such n's, you will of course get one n that will exceed n plus 1, because below n plus 1 there are only finitely many natural numbers. The infinitely many n's cannot be accommodated there. There is not enough space. So some n must exceed n plus 1. But at the same time, because the other n's that you see that come, I should not say before, but in the sequence nj, they appear before n plus 1, that is n naught, n1, all these things. So this n you should also be able to choose one such n which is also none of these things. Note one thing carefully, that just simply assuming that n is greater than n plus 1 does not automatically tell you that n is also not equal to these other n's, because we have only proved that this sequence is strictly increasing. We have this. Now we don't exactly know what the statuses of these other n's are with respect to these n's. I cannot say that n naught actually is smaller than these things. I don't know, because I have only proved that this sequence is strictly increasing. So that's why I have to impose this extra condition. Okay. But now such an n being greater than this means what? In our sequence n plus 1, n plus 2, this n will lie between two such terms. Always there will be two such terms, between them this n lies, that is two such ni's, ni and ni plus 1, that are the closest. Between them n sits. Then n plus I is less than n, which is less than n plus I plus 1 for some positive natural number I. This has to happen. And note that we have strict inequalities because n cannot be equal to any of these ni's. All the things that you see here that start from n plus 1. Okay. Now this implies that n belongs to a minus okay. Now watch this carefully. N is already of course coming from a minus, and n is not equal to any of these. We have this now. So because n is greater than n plus I, and due to the increasing nature of that sequence, n is not equal to any of these previous things. But we can go further back than this, right? n minus 1, what about these things? So that is taken care of by this extra condition. N is also not equal to the other n's, okay, that come before n plus 1, that is starting from n minus 1 and so on. Okay. So now we go back to case 1 and case 2. So you see that this n is here, n belongs to this, thus n should be greater than or equal to the minimum of this set. minimum of A minus difference n plus I, sorry. And since we know that all these terms, I mean the next one also, n plus I plus 1, they are coming from A minus. So by case 2, this minimum is nothing but n plus I plus 1. And this is a contradiction because n is greater than or equal to n plus I plus 1, and here you have n less than or equal to n plus I plus 1. And to get rid of this contradiction, we have to conclude that our first supposition must be wrong. So, our initial supposition must be wrong, i.e. case, so our supposition was that case 1 occurs only finitely many times, so which cannot be true. Case 1 must occur infinitely many times. Similarly, you can understand that exactly similarly one can prove that case 2 also occurs infinitely many times. You just have to switch the roles of A plus and A minus and all the other things. Infinitely many times. So this answers the fourth why query. After this also we have some other whys that we will see answered in the next analysis update. That means this coming Sunday. So I am just going to stop things here itself. Our next upload is this coming Tuesday, and on Tuesday let us go back to number theory, where I think only one exercise is left in our Diophantine equation, that section. So with that, on Tuesday we will be able to complete that, and then after that we will see what is the next chapter. I think it involves primes. So things are going to get interesting. The boring parts are almost over. So see you on Tuesday with that. Until then, this is me, Lucifer from a mathematical room. Have a nice day.